Chem 106, Chapter 19, Electrochemistry, Lecture 1. The first part of the chapter deals with oxidation states and oxidation-reduction reactions. Chemical reactions in which the oxidation state of one or more substances changes are called oxidation-reduction reactions, which we really just call redox reactions. Red for reduction, ox for oxidation. Oxidation involves the loss of electrons. You can remember that oxidation is lost oil and increases a substance oxidation number. Reduction involves the gain of electrons. Reduction is gain, rig. So the mnemonic oil rig. Oxidation is loss, reduction is gain, and therefore reduction decreases a substance's oxidation number. Electrochemistry is the branch of chemistry that deals with the relationships between electricity and chemical reactions. So if we, if we consider the spontaneous reaction that occurs between zinc and hydrochloric acid, and again, the chloride is simply a spectator, so we leave it off. So it's really the reaction between zinc and the hydrogen ions. What we end up making then is zinc ions in solution from the solid zinc metal, and we liberate hydrogen gas. The oxidation number of the zinc and the H plus have changed. Zinc has its oxidation state on the left is 0, but on the right it is a +2. So it's increased from 0 to +2. Therefore, it has lost electrons, so that is oxidation. The H plus, its oxidation is 1+, and hydrogen gas has an oxidation state of 0, so it's decreased from +1 to 0. So therefore, the hydrogen has been reduced. The hydrogen ion has been reduced to molecular hydrogen. Zinc is oxidized from zinc 0 to zinc 2+. H plus is reduced to molecular hydrogen. Now, the word agent is simply a word that means acting on behalf of. And so hydrogen ion is the oxidizing agent because it is causing the oxidation of the zinc. It's acting on behalf of the zinc for oxidizing. And so and another term for that is oxidant. So H plus is the oxidizing agent or oxidant, since the H plus causes zinc to be oxidized. On the other hand, zinc is the reducing agent because it acts on behalf of reducing the hydrogen ion. And so another term for reducing agent is reductant. So zinc is the reducing agent or reductant since zinc causes H plus to be reduced. Now, the final notation here is that the oxidizing agent is always reduced in the process. The reducing agent is always oxidized in the process. So keep it straight about what term means what. An oxidizing agent causes something else to be oxidized while it itself is reduced. A reducing agent causes something else to be reduced while it itself is being oxidized. All right, a big chunk of this chapter is balancing redox equations. In General Chemistry 1, or before, you learned how to balance chemical equations according to the law of conservation of mass. Because then the amount of each element present at the beginning of the reaction must be present at the end. And so you, what we call mass balanced all those equations, and that was fine. But when we talk about redox equations, then there's more to it. It's not just a matter of mass balancing an equation. You must also charge balance an equation. Conservation of charge. Electrons are neither gained nor lost in a chemical reaction, so they must also balance out in the end as well. For all non-redox, electrons aren't really going anywhere, and so they're not a concern. But in redox, electrons are actually changing places in substances, and so they must be accounted for the same way as the mass balance must be accounted for. So mass balance and charge balance are very important for redox equations. And so they require more work, of course, as I just said. So there are two ways to look at this, that redox reactions frequently happen in either acidic solution where you've added hydrogen ions to take part in the redox reaction, or in basic solution where you've added hydroxide to do it. But let's walk through how to balance redox reactions in acidic solution first, because that's the easier of the two. And so these are the steps that we go through here that you can read. You're going to divide the given equation into two half reactions, find the like species, same central atom on each side of the equation, and write them as a separate equation. Then one of the equations will be an oxidation half reaction, the other will be a reduction half reaction, because those are complementary. There must be one of each in order for this to be a redox equation. Then separately, you're going to mass balance each half reaction, and then you're going to separately charge balance each half reaction according to these statements. And oxygen is always a pain, as it always was for the mass balance way back when. But mass balance first, then charge balance each half reaction according to these statements. And we're going to do an example so you'll be able to see and follow step by step through it. Then you're going to algebraically add the two half reactions to get a proper whole equation. So you're going to take the two half reactions that you've now mass balanced and charge balanced and algebraically put them together. The electrons must cancel out. So you may end up having to multiply each half reaction by some coefficient that allows for the electrons to disappear. So the only requirement is once you mass balance and charge balance each half reaction, you must then ensure that the number of electrons for each half reaction are equal so that they cancel out when you algebraically combine them. So now, once you put that together, they're mass and charge balanced. So let's do a lecture problem on this. Lecture problem 1. And there's my pen. All right. If you look at lecture problem 1, it says, balance the following redox reaction in acidic solution. Okay, so when we do that, let's look at the original equation and see why we can't just balance it as is. We have molecular iodine plus hypochlorite, and that's going to yield iodate plus chloride. All right. So now what we could do is, why do we have to look at all this? Why can't we just balance it? And so we see that there's two iodines here, and so I'm going to use a different color here. So there should be a 2 there, right? And there are 6 oxygens now, so there needs to be 6 here, and that makes 6 chlorides, so 6 here. And now it's all balanced, right? 1, 6, 2, and 6. Why not, right? Well, even though it's physically mass balanced, look at the charges. On this side, you have 6 minuses total. On this side, you have 2 minuses here and 6 minuses here, which add up to 8 minuses. And it's due to electrons, so I wrote an E there. So that's not charge balanced. So this doesn't work. This won't get us to where we need to be. All right, so let's go back then and look at this again from the point of view that we need to balance this properly, because even though we can mass balance it, that wasn't properly charge balanced. So let's write this equation again as a starting position here. Molecular iodine, plus hypochlorite is going to yield iodate and chloride. All right, so step 1 is to break it into half reactions. And what we want is the same central atom. So for this, that's going to involve the iodine and the iodine-containing species on this side. Here is the chlorine-containing species and the chlorine-containing species. So we've got 2 half reactions. All right, so let's focus on the iodine then. So I2 solid is going to end up going to IO3 minus aqueous. All right, so the next step then is going to be then on the side, you see how one side has O but the other side doesn't? So we need to add water to make this work. Oops, let me leave a little bit of room there because we need coefficients eventually. All right, so now we've got iodine, oxygen, but now I've made a problem with hydrogen. And so this is about the only place where you're actually going to use H pluses rather than H3O plus. And it's understood that it will be bound to water, but for balancing redox equations, it is simple. It is a simplified way to go ahead and leave it as H plus, even though we know it's really H3O plus. We're going to write it as H plus for simplification on balancing. But do understand there is no such thing as H plus floating around in solution. All right, so now, because in order to balance an equation, you have to have the same kinds of elements on both sides, and now I have iodine, hydrogen, and oxygen on the left, iodine, oxygen, and hydrogen on the right. Now I can mass balance it. So there's 2 iodines, so I'm going to try a 2 there, right? That's going to give me 6 O's, and that's going to give me 12 hydrogens. So 1, 6, 2, 12. Okay, so do you agree that this is mass balanced then? 1, 6, 2, 12. Looks like it is to me. All right, let's go to the other equation before we charge balance. Let's go to the other equation first, where we have hypochlorite, and that somehow is going to go to chloride. Again, one side has O, but the other does not. So we know we have to put water on this side to get oxygen onto the right, but that makes H on the right but not on the left, so we're going to have H plus here as well. All right, so now we have OClH, ClHO, good. Now we can mass balance the second half reaction. There's 1 O, there's 1 Cl, but there's 2 H's, so I put a 2 there. So 1, 2, 1, 1. That looks good, right? Okay. Now, we need to charge balance each of them. And so what we look at is the charges on each side. So if I go back up here to this first one with the iodine containing reaction, on the left, there is 0 charge. But on the right, I have 2 negatives and 12 positives. So again, coefficient and superscript here. There's 2 negatives and 12 positives, which gives me a total of 10 pluses. This is 0. This side has 0 charge, but this side has 10 pluses. Now all I can do is add electrons to reduce the number. If I add electrons here, it's going to go from 0 into negative, and that'll never equal 10 positives. So the only way I can make this work is, since this side is 0 and this is 10 positives, I must add 10 electrons here, because 2 negatives and 10 negatives, that's 12 negatives, and this is 12 positives, makes this 0 and this side 0. So that's how that works. Now, on the second equation here, I have 1 minus and 2 pluses, which gives me an overall 1 plus, and this side has a 1 negative. So the only thing I can do is add negative. So my goal is to get to the lesser here, which is 1 negative. This is 1 plus, and I want to get to 1 negative. So I'm going to have to add 2 electrons here. So 2 negative, 3 negatives, and 2 pluses gives me a negative, and this side still has a negative. All right. So while we're at it here, I need you to understand too then that which is oxidation and which is reduction. Oxidation has the electrons on the product side. So this is the oxidation. Oops, got to change colors here. Because the electrons are on the product side, this is the oxidation half reaction. The iodine is being oxidized to iodate. The equation that has electrons on the reactant side then is the reduction. And so we're going to use those electrons to reduce the hypochlorite to chloride. So you need to be able to label the 2 half reactions. Once you get them charged or mass balanced and then charge balanced, if the electrons, and remember this is a complementary pair, so if you end up with electrons on the same side, something's not right. But for the oxidation half reaction, electrons end up on the product side. For a reduction half reaction, the electrons are on the reactant side. Okay, next step. We need to algebraically add these together such that the electrons disappear. But because there's 10 electrons in the oxidation half reaction and only 2 in the reduction half reaction, and we need them to be equal, then what we can do is multiply this reduction half reaction totally by 5. Because 5 times 2 gives me 10 electrons, plus 5 hypochlorites, plus 10 H pluses, yields 5 chlorides, plus 5 water. And so now this needs to be crossed off, and we need to focus on this. So we need to algebraically combine this equation and this equation. Because now we can see what's the same goes away. The 10 electrons now can go away. And the only other things that we worry about are the water and the hydrogen. So again, we still had 1 iodine. So that didn't change out front. Plus, and now we have 5 OCLs from this one. And so let's look now. We have 6 waters here and 5 waters here. So these completely go away, and that coefficient goes away. 5 goes away totally, leaving 1 up here. So that's going to be plus H2O, liquid. All right, now the hydrogen ions. Notice there's 12 on the product side in this oxidation half reaction, but only 10 here. So these 10 completely go away, leaving us with 2 on the product side. So all that's left on the reactant side is 1 iodine, 5 hypochlorites, and 2 waters. Arrow. And then let's see what's left over here. We have 2 iodates, aqueous, plus 5 chlorides, plus 2 hydrogen ions. And now it doesn't matter which order. As long as they're on the correct side, it doesn't matter whether you put the 5 hypochlorites before the iodine and the water and so on, as long as you have that many of each kind on each side. And so let's double check here. Yes, iodine, 5 hypochlorites, 1 water, 2 iodates, 5 chlorides, and 2 hydrogen ions. Everything is balanced. Everything looks great. This is the balanced equation, the balanced redox equation for what happens when you put iodine and hypochlorite together in acidic solution. This is the balanced redox equation. So let's do another one, except that let's go back to the outline real quick, because the next one is going to be in basic solution. And so just a little ideas here about this. So for balancing redox equations in basic solution, you're going to follow all the same steps as you did for balancing an acidic solution, including the addition of hydrogen ion. So we're going to treat it, even though the direction, the question itself says it's in basic solution, for the beginning, let's just pretend that we're doing it in acidic solution and we're going to use H plus and water instead. Then, once the equation is both mass balanced and charge balanced, we will then bring hydroxide in, which will cancel out the hydrogen ions to make water. And then once we've canceled out the hydrogen ions to make water, then we can figure out how to cancel the water, and that'll just leave hydroxide on one side and water on another. All right, so let's try this then with the second lecture problem. All right. The second lecture problem then says balance the following redox reaction in basic solution. And so that's going to be permanganate with bromide to make manganese dioxide plus bromate. All right. So again, just like before, we're going to break this into 2 half reactions. And so the manganese containing species and the bromine containing species. So let's focus first on the manganese. So we have MnO4 aqueous, and there's a minus on that, is going to somehow yield MnO2. All right. Now, notice that we have oxygen and manganese on both sides, so oh no. They already both have manganese and oxygen, because remember our trick in the first problem was one side had oxygen, one didn't, so we brought in water. Well, now notice since there's both still one manganese, but this one has 4 oxygens and this has 2 oxygens, the only way I'm going to get them to ever balance out is by simply increasing the oxygen on one side versus the other. So I'm going to add water to this side to get oxygen to be able to increase over here. Now, I'm not going to mass balance it just yet. I just want you to see that I need to add oxygens onto this side, and the way I add oxygens is through water. Now, I've introduced hydrogen there, which means I have to put hydrogen ions here. All right, so now manganese, oxygen, and hydrogen, manganese, oxygen, and hydrogen. It's good. So now we can mass balance. 1 manganese, but 4 oxygens, so I'm going to need 2 waters here, which means I'm going to need 4 hydrogen ions here. Oops. Do that again. 4 hydrogen ions there. So 1, 4, 1, 2 are the numbers I have for that half reaction. Good. And then let's go ahead and charge balance it too. All right, and so I have 1 minus and 4 positives, which means this side is overall 3 positive. This side, there are no charges. So the only thing I can do is reduce charge by adding electrons. 3 pluses, nothing, 0. So the only way I'm going to get rid of that 3 pluses is to add 3 electrons. So 3 minuses, 4, that makes 4 minuses, that's 4 pluses, that makes 0. This is 0. Now this equation is, this half reaction is balanced. And tell me, we added electrons as a reactant, so which half equation is this now? Yes, it is the reduction half equation because electrons are reactants. All right, let's focus on the other equation where we had bromide, that is going to turn into bromate. All right, so again, no oxygen here, but oxygen here. So we know we're going to have to add water to this side. And because now we've introduced hydrogens, we're going to have hydrogens on this side. Okay, so Br, HNO, Br, HNO. So now we can mass balance this. There's 1 bromine on both sides. 3 oxygens here, but only 1 here, so I'll make this a 3. 3 times 2 for the hydrogens is 6. So 1, 3, 1, 6. And that's what I get. Good. Okay, just double checking to be sure. And now we're able to charge balance. 3 negatives on this side and 5 pluses on this side. 3 negatives, 5 pluses. So we're going to have to come down to this side to make this all work, right? Or I'm sorry. Let me back up here. I can't believe I goofed that. There's only 1 minus. That's 0 charge, sorry. So 1 negative on the left, but 1 negative and 6 pluses makes 5 plus. So we're going to go from 1 negative and 5 plus. So I have to bring the plus side back down. In order to get from 5 plus to 1 minus, I'm going to have to add 6 electrons. Now, that cancels this out and makes that minus, and that's minus, so now good. This half reaction is balanced as well, both charge and mass. And since electrons are product, this must be the oxidation half reaction. Okay? And now we want to algebraically add them together, and notice I've got 6 electrons here and 3 electrons up here. And so, I'm going to have to multiply this equation by 2. This whole thing has to be multiplied by 2 to make it work. And so I'm going to bring this down here and rewrite it. That gives me 6 electrons plus 2 permanganates plus 8 hydrogens, and that yields 2 MnO2 plus 4 H2O. All right, so hopefully if I've done that right, that comes out to be that. All right, okay, so now we're ready to balance this thing. And so we're going to use these two to balance. The 6 electrons goes away just like they should. 3 waters completely goes away here because there's 4 here, and so we just cross that off, leave that 1. There are 6 hydrogens here, it goes away, canceling out that, and that leaves 2. Because there were 6 here and 8 here, so that leaves 2 down here. So we've canceled out everything that cancels, and so in order to balance this, then we have 2 MnO4 aqueous plus 1 bromide, and that's plus 2 H plus, yields 2 MnO2 solid plus BrO3 minus plus H2O. 2 MnO4s plus Br minus plus H2O. What am I missing? Or no, plus H plus, sorry. Yeah, okay, here we go. I'm sorry. I just want to make sure that we're doing this correctly before we go any farther. All right. So again, and we can even be sure to mass balance. There's 2 manganese, 8 oxygens. That's 4, 5, 6, 7, 8 oxygens, 1 bromine, 1 bromine, 2 hydrogens, and 2 hydrogens. So we know it mass balances in the end, and 2 minuses, 3 minuses, and 2 pluses. So that's 1 minus overall here, and 1 minus overall there. Yes, this is a good equation, provided it was balanced in acid. But the question says balance it in basic solution, so we need to do hydroxide. So what we're going to do is we're going to add hydroxide to it, to both of this, because algebraically what you do to one you must do to the other. But my goal is to cancel out the H plus. So what I need to do is I need to add 2 hydroxides here, right? That makes this into water. 2 H pluses plus 2 hydroxides makes water, which means then that I need to add 2 hydroxides to this side as well, because what you do to one, you do to the other. So this is going to turn into water. So I'm going to end up with 2 MnO4 minus aqueous plus the Br minus aqueous plus 2 H2O liquid yields 2 MnO2 solid plus the bromate BrO3 minus aqueous plus H2O liquid plus 2 OH minus aqueous. Now, notice here again, we've made 2 waters here and 1 water here, so that's going to cancel away and leave just 1 on this side. So now I'm going to erase some stuff up here because I'm out of room. So if it's all right, I'm going to erase up here to make some final room for this. And bring this up. All right. So now my final equation, 2MnO4 minus aqueous plus bromide, aqueous plus H2O liquid, because again, there's still 1 left because there was only 1 over here but 2 here, and they canceled 1 away, so that leaves 1 here, yields 2 MnO2 solid plus BrO3 minus aqueous plus 2 hydroxide aqueous. And that should be the final equation. 2 permanganates plus bromide plus water yields 2 manganese dioxides plus 1 bromate plus 2 hydroxides. And now, again, you can look at it and it'll still mass balance and charge balance as well. And this is the final answer to the second question. This concludes Lecture 1.